Let's talk about solving systems by row reduction. We can use augmented matrices to solve systems of linear equations. The aim is to get them in row echelon form or reduced row echelon form by using elementary row operations. For example, solve x plus y plus z equals 6, 2x minus y plus z equals 3, 2y minus z equals 1. Representing this with matrices, we have this. 1, 1, 1, 6, 2, negative 1, 1, 3, 0, 2, negative 1, 1. Now notice there's no x over here, so the coefficient of x is 0. Using elementary row operations, we want to get that matrix to look like this. This would tell us our solution, because notice we basically have x equals such and such, y equals such and such, z equals such and such. Boy, that would be easy. We want to get the matrix in what's called row echelon form. Here's what that looks like. And again, this looks complicated, but you'll get the hang of it. First, if a row does not consist entirely of zeros, then the first non-zero number in the row is 1. This one is called a leading one. The position with the leading one is a pivot position, and that column is a pivot column. Next, if there are any rows that consist entirely of zeros, then they are grouped together at the bottom of the matrix. Then, if two successive rows do not consist entirely of zeros, the leading one in the lower row is further to the right than the leading one in the higher row. So for example, is this matrix in row echelon form? Here are the criteria. If a row does not consist entirely of zeros, then the first non-zero number in the row is 1. Yeah, this is fine. Oh, this one's not. Look at that. That's not a 1. So the answer is no. How about this one? If a row does not consist entirely of zeros, the first non-zero number in the row is 1. Yeah, we're good there. Yeah, that's good. And yeah, that's good. That's great. If there are any rows consisting entirely of zeros, they're grouped together. That's irrelevant. If two successive rows do not consist entirely of zeros, then the leading one in the lower row is further to the right than the leading one in the higher row. Oh, no, that's not what we have here. The leading one here, the leading one in the lower row, that should be to the right, further to the right than the leading one in the higher row. So yeah, you'd have to interchange those two rows. So the answer is no. How about this? The first non-zero number in each row is 1. If any rows consist entirely of zeros, they're grouped together at the bottom of the matrix. That looks good. And if two successive rows don't consist of zeros, then the leading one in the upper row is further to the right than the leading one in the lower row. Yeah, that looks good. So that one's yes. How about this? Yes, you'll find it meets all the criteria. Reduced row echelon form satisfies the above three properties and also this property. If there are any entries in a column above a leading one, they are all 0. This matrix is in row echelon form. Is this matrix in reduced row echelon form? Let's look at the criterion. If there are any entries in a column above a leading one, they're all 0. Gosh, this is a leading one. That's not 0. These aren't zeros either. That's no. How about this? If there are any entries, again, this matrix is in row echelon form. Is this matrix in reduced row echelon form? Does it satisfy this last criterion? If there are any entries in a column above a leading one, they're all 0. The answer is yes. These are entries that are above a leading one, and they're all 0. How about this one? Is this in reduced row echelon form? Yes. So getting a matrix in row echelon form by using elementary row operations is called Gaussian elimination. Getting matrix in reduced row echelon form by using elementary row operations is called Gauss-Jordan elimination. These procedures are named after Carl Friedrich Gauss, one of the greatest mathematicians of all time, and Wilhelm Jordan. These, remember, are the elementary row operations. Interchange two rows, multiply a row by a non-zero constant, add a multiple of one row to another row. So for example, let's solve this system of equations we looked at a moment ago using Gaussian elimination. So first we represent it as a matrix, and now we're going to apply elementary row operations. First, find the leftmost column which is not all zeros, and that would be this column. We need a non-zero number for the top entry in this column. If necessary, interchange the top row with another row in order to obtain this. Okay, we have a non-zero number. That's a 1. That's fine. Don't need to interchange. If this top entry is not a 1, divide the entire row by this entry so that this top entry is then a 1. This one is a leading one. Well, we don't need to do that because we have a 1 over here. If, for example, we had a 5 there, then we would have to divide that first row by 5. To convert the entries beneath the leading one to zeros, add suitable multiples of the top row to the rows beneath it. So in other words, we're going to use this 1 to kill off the stuff underneath it. We're going to multiply row 1 by -2 and add it to row 2. So I like to write the numbers above because it is so easy to mess up the algebra of matrices. So multiply row 1 by -2, and we end up with -2, -2, -2, -12, and let's add that to row 2. When you add these to these, here's what you end up with. -2 plus 2 is 0, -2 plus -1 is -3, -2 plus 1 is -1, and -12 plus 3 is -9. So this is what we end up with. So now we've dealt with this row, so we're good with that. That column's dealt with. So now we ignore the top row and we apply the above steps to the resulting matrix below it. So now we're gonna work on this matrix. So again, as before, we want this to be a leading 1. So we'll multiply row 2 by -1/3. And we end up with this. So -1/3 times row 2. That's going to give us this row. So we'll end up with 1, 1/3, 3. Okay, and then we use that 1 to kill off the 2 beneath it. So -2 times row 2 added to row 3. Again, -2 times this row added to row 3. So this is what row 2 looks like after you multiply it by -2. And now let's add it to row 3. We'll end up with this. -2 plus 2 is 0. -1 plus -2/3 is -5/3, and -6 plus 1 is -5. Okay, we're almost there. So these two rows are great. Now we need to work on this row here. So -5/3, yeah, that's not a leading 1. We need to multiply that by -3/5, and now we have a leading 1. So, yep. And we're good to go. This matrix is now in row echelon form. We would use back substitution to solve the system of equations. The system of equations we get is x plus y plus z equals 6, y plus 1/3 z equals 3, and z equals 3. Again, this system is going to have the same solution as the original system. So z is 3. Gosh, that's pretty easy. So z is 3. We use that to figure out what y is. Y plus 1/3 z equals 3. Y plus 1/3 3 equals 3, in other words. Y plus 1 equals 3. That means y equals 2. X plus y plus z equals 6. Plug in y equals 2 and z equals 3. And we end up with x plus 2 plus 3 equals 6. X plus 5 is 6. X equals 1. Thus, our solution is x equals 1, y equals 2, z equals 3. 1, 2, 3. Let's solve this system using Gauss-Jordan elimination. Again, what we want to do is get the matrix in reduced row echelon form. If there are any entries in a column above a leading 1, they're all 0. So we just finished Gaussian elimination. We get it in row echelon form. Now we're using Gauss-Jordan elimination to get in reduced row echelon form. Again, any entries above a leading 1, we need to make these zeros. So we need to get rid of this guy and this guy here. So since we want the matrix to also be in reduced row echelon form, we also do the following. In the last non-zero row, use the leading 1 to convert the entries above it to zeros by adding suitable multiples of the row to the rows above it. So this is the last non-zero row. We're going to use this 1 to convert the entries above it. So we're going to use that 1 to kill off the entries above it, and we know how to do that. First, let's get rid of this guy. So -1 times row 3 added to row 2 is going to get rid of this guy. -1/3 times row 3 will give us 0, 0, -1/3, -1, and then let's add that to row 2. So we end up with 0, 1, 0, 2. That's great. Now let's get rid of this one. So negative row 3 added to row 1. We're going to use this guy to kill off this guy. Again, I like to write this. So negative row 3 is going to be 0, 0, -1, -3 added to the top row. And this is what we end up with. So 1, 1, 0, 3. Great. We've converted both of those to zeros. Working upward, repeat the above step for all the non-zero rows of the matrix. So we've used this one to kill off the entries above it. Now let's use this one to kill off the entries above it. So we need to add the opposite of row 2 to row 1. This is what the opposite of row 2 looks like. 0, negative 1, 0, negative 2. Add it to row 1. Negative 1 plus 1 is 0, 0 plus 0, 0, and negative 2 plus 3 is 1. So you end up with 1, 0, 0, 1, 0, 1, 0, 2, 0, 0, 1, 3. And we're done. This matrix is in reduced row echelon form. And see how easy it is to read off the answer. X equals 1, Y equals 2, Z equals 3.